The next one. Let's rediscuss about automatic control means with one slide. That is this slide here. No, actually, no, there's a little bit more slides. Sorry. This is more slides, but I was actually remembering. Tell me if we are together with the stuff here. Very much together, not together at all. I'm missing something. What are you missing? You are missing context. No worries. So, basic Newtonian mechanics, the car should be clear. This one we should be clear at this point what we mean with ODE. Discretization we know, and input-output disturbance, we got the point. Okay, you know this stuff. I'm pretty sure 100% that you know this stuff here. This is a car. Those are parameters of the car. And as we were seeing before, we can make from Newton laws something that looks like this stuff here. True? What does automatic control mean? If I want the speed of my car to be constant in time, I might have a person that is there accelerating and braking. Or I might want to do some algorithm that given x dot computes u. True? This means doing an automatic control. We might also consider discrete time versions of this stuff here, but let's ignore for now. Let's work in continuous time. We might do all the considerations in discrete time. Let's stick on continuous time for now. Are we together that this one is our control objective? We want to be as close as possible to 70 kilometers per hour, 90 kilometers per hour, whatever we want. We want that that E to be as small as possible. And something that we might do is basically what is called a feed-forward controller. That means I think I know my car. That means I think that the ODE that I built of my car is a good descriptor of my car, and I can use it to kind of compute quantities with good approximation, good enough approximation. And I think I know that in 500 meters, I go from flat to 5% of the name slope. Together? That means that in a certain sense, your computer knows that in some seconds, it's gonna meet more resistance in a certain sense because there is gravity, but the computer knows also the ODE. That means the computer can forecast the effect of gravity on the car because the ODE works as a predictor. True? So the controller might say, I know what is going to happen. I know how my plant behaves because I've got a good enough ODE. I'm planning a U that at a certain point is going to do something like this, my U, to compensate. True? Because the computer knows. I know that a ball is hitting me. True? I don't see it, but I know that it's going to hit me. I move. True? Together? This is something that you can do. It's a controller. It's a way of programming a computer such that the man is not on the loop. What are the problems? I need to agree with this one. If the forecasted disturbance is different from the disturbance that will actually happen, that means that I think the ball is coming, but actually the ball is coming in 10 seconds, or it's coming 5 seconds before I start moving. D hat, what the computer thinks, D, what is going to happen. If that is big, already a problem. True? Another problem, if my ODE is a bad forecaster, if my ODE tells me that increasing my, how do you say, pedal angle of 1% is going to compensate, but actually I need 5% of angle speed more to compensate. If I've got an ODE that is not accurate enough, the worse the ODE, the bigger this one. The worse the forecast that I have on the disturbance, the bigger this one is. Are we together? Do you see the effects? Feed forward means I use my model to compensate, and I use my forecasts of the disturbance to compensate. And what's out terms? The terms are slightly different. I think that sometimes people tend to confuse feed forward with open loop. Feed forward means that the controller has a knowledge of what is going to happen and does something. Open loop means I just go. It's like I think I know the road, and I plan that at noon I will speed up a little bit, and at 12:15 I will slow down a little bit without accounting for measurements of any kind. Together, feed forward and open loop are two different things. Are we together? It's if you incorporate forecast of the disturbances or not. I am somebody that is planting tomatoes. Open loop means the 1st of June I'm gonna plant. Feed forward means I will plant on the 2nd of June because I've got the forecast, the weather forecast 1 week before that I was saying that the 1st of June is going to be rainy. You see? Together? Slightly different terms. And in a certain sense, it's kind of a simple way of controlling. I have an ODE, I might have a forecast, and depending on those two factors, I do decide, I program the computer so that it does something on how much to act on the car. Are we together on what they mean? 1, 2, 3. So, read and answer. Discuss and answer. What do you think, people? What would you say? Very much false. Let's make a practical example. I am building the gate, the automatic gate of my house. That means that I'm gonna have an object that moves with a certain angle from closed to open and vice versa. And I would like it to move with a certain angular speed in time. In time, I've got my theta dot reference. That is, whenever I click open, my speed should go like from 0 to 2 degrees per second. I don't know, a little bit slow. 5 degrees per second might be too fast, but you got the point. A certain angular speed, and then it closes. True? Or stops wherever it is. If I have a data sheet of my motor, and I know how much the inertia, the angular inertia of my gate is, I kind of make an ODE. True? Perfect. If I make a controller, the controller will kind of open loop controller the controller will assume to know the motor, and will assume to know this one, and somehow, whenever I actually implement the stuff and try out, for sure my speed is going to do something that is slightly different. So instead of 5 degrees per second, assuming that the data sheet and the ODE is kind of meaningful enough, I might have 5.5 degrees per second. Might be okay? No? Might be perfectly fine. I don't need to buy anything more. I'm sensor to kind of measure the error. This way of working for cheap stuff and simple stuff, for which the performance, even if you've got a 10% performance change, like a delta of the performance that you expect, 20%, depending on the situation, you might want to have something that is very simple. True? If you have a rocket and you want to send a rocket to Pluto, I don't think that the open loop controller is going to work. True? We are going to need to do what? Compare our measured behavior with what we would like to happen, compute some error, and decide depending on the error. True? What is the problem of this? This means that I need a sensor. If I want to compute the difference between what I expect and what is happening, I need to know what is happening. It means I need to buy a sensor. I need to cool it. I need to wire it. And see, it's more meaningful for more advanced performance to include a feed forward. That means detecting this error. But detecting the error means computational complexity, hardware complexity, higher costs. We are engineers. We don't do overkills. We don't shoot with an atomic bomb to a mosquito. True? Together? Are there questions up to now before going on? Are there questions up to now? And then let's do 2 dedicated videos because I think you're going to use them